and welcome, and in this video we're going to be talking about graphing piecewise functions. So what is a piecewise function? Well, you're looking at one. Alright, a piecewise function is actually a special type of function that is made up of pieces of other functions, okay, what we could refer to as subfunctions. So if we're looking at this piecewise, this is an example of a piecewise. We generally have this kind of curly brace here, and inside the curly brace is our subfunction. So these little pieces right here, this is what we will call our subfunctions. And then you might see this part be a little bit different. Sometimes people just put a little comma here. Sometimes it says if, but afterwards you're going to see a set of inequalities, maybe even just an equation like x equals 4 or x cannot equal 4, okay? And what we call these is the constraints. Okay, so we have a piecewise function that is made up of other functions called subfunctions and constraints. Now reading this might be a little bit confusing, but I'm going to go ahead and break it down for you. This graph is going to look like pieces of different other graphs, okay? And it's all based upon what the constraints are for that particular subfunction. So, for example, I'm going to take a look and break down our first subfunction. So I'm going to break down the one in blue. So what this graph is, this is telling us to graph, and I'm going to write it out for us, okay? This is telling us to graph the function y equals x plus 1 only when x is less than or equal to -2. So let me go ahead and write that out for us. Okay, so what we're going to do is we're going to graph y equals x plus 1 only when x is less than or equal to -2. So there's actually a couple different ways we can do this. We can make a table of values. So like if I wanted to, I can make a table of values and just plug in values of x that are less than or equal to -2. So I can plug in -2, -3, -4, find my y values and plot those points, okay? But what I'm going to do is I'm actually just going to go ahead and graph this entire function, okay? So give me a second. I'm going to graph this entire function over the entire coordinate plane. Okay, so that would be the graph of y equals x plus 1 if there were no constraints, no conditions, okay? But here's the thing. We can only be having this graph when x is less than or equal to -2. So what I'm going to do is I'm going to get rid of all the values when x is not less than or equal to -2, all right? So x is less than or equal to -2 to the left of -2. So x is -2 right here. I do see some people kind of draw like a line like, okay, this is where it gets split up when x is -2. Feel free to do that, but I recommend that you erase that after you get the graph done. Otherwise, it looks a little bit confusing and could actually be misconstrued as being an extra line, which would be incorrect. But what I'm going to do is I'm going to get rid of all of that, okay? And I'm actually going to get rid of this as well, okay? And now it's when x is less than or equal to -2. Now the or equal to is actually a really important piece of information. So what that's saying is all the way up to when x is -2 and including -2, the graph is going to be y equals x plus 1. So to show that, we are going to put a big closed circle on -2 when x is -2. And what that's signifying is that the graph actually exists at that point, okay? If it was not equal to -2, if it was strictly less than, then we would show that with an open circle, okay? And we're going to see that with this next function, because what this next subfunction is, this is saying, hey, graph y equals -2x plus 4 only if x is greater than -2. So I'm going to go ahead and write that out. So we're graphing y equals -2x plus 4 only if x is greater than -2. So once again, you can make a table of values and plot those points. I'm going to go ahead and graph the entire function. Okay, so this would be if we were just graphing y equals -2x plus 4. The only thing is that it's only if x is greater than -2. So I'm definitely going to have to get rid of when x is like -3 and -4 and stuff like that. However, I don't actually want to get rid of entirely when x is -2. The reason, if a common mistake is that some people will just start when x is -1. But the thing is that you're actually eliminating all of the possibilities in between -2 and -1, because there's actually an infinite number of numbers in between -2 and -1, and we need to show that. So the way that we signify that it goes up to negative when x is -2 is we actually are going to use an open circle. And what that open circle is saying is, hey, the graph starts immediately either after or stops immediately before. In this case, it's saying, hey, it starts immediately after x is -2, okay? So that way we don't lose all those decimal values in -1.9987, so on and so on, okay? So that is one example. Let's go ahead and take a look at another example. Okay, so we have a new example here. And with this function, we actually have 3 subfunctions. So in the previous example, we only had 2 subfunctions, so you may have noticed that we had 2 different pieces on the graph. In this example, we have 3 subfunctions, so we're actually going to have 3 different pieces on the graph, okay? And that should kind of make sense. So I'm going to graph each individual piece. So the first one I'm going to graph is y equals -x plus 3. And I'm only going to be graphing this if x is less than -4. Now remember, like I said, you can make a table, you can graph the whole thing, and then get rid of what you don't need. And that's kind of what I like to do personally. So I'm going to go ahead and do that. So that is our first piece of the graph. That is the graph -x plus 3 if x is less than -4. So you should see that since it's not equal to -4, it's strictly less than, that we do stop at -4, but we use an open circle and not a closed circle. So that would be our first piece of the graph. Now we have to graph y equals 1/2 x minus 4 if x is in between -4 and +2. Now this one's going to be a little bit different. This is just going to be kind of a line segment, okay? All the other examples, you have seen arrows on the end because they continued forever in that respective direction. This one is saying, hey, we're only going to exist when x is greater than or equal to -4 and less than 2. So we're actually going to have a starting point and a defined stopping point. So let's go ahead and graph this one. Okay, and before I even connect any of these points, I'm actually going to get rid of now what I do not need. So it starts when x is -4. It starts when x is -4 and it's or equal to, so I'm going to use a solid circle on that. So x is -4 here, so I want to get rid of these two, and let me fill that sucker in a little bit more so we know, yeah, that we start there, okay? Now it ends when x is 2, all right? It goes to when x is 2, it has to be less than 2. Notice it is not or equal to, so I'm gonna have to end with a open circle. So when x is 3, I get rid of it, 4, 5, so on and so on and so on. And now I'm gonna have to get rid of this point actually and redo it with an open circle, because it was not or equal to when x is 2. When x is 2, it is not or equal to, so it's an open circle. So now I'm going to connect these. And there is our second piece, okay? But we still have one more, and that is y, oops, wrong color. That is y equals 3. So we're graphing y equals 3 if x is greater than or equal to 2. Remember, that is just a perfectly horizontal line when x is, or when y is 3. Because y is 3 here, y is 3 here, y is 3 here, and so on and so on. Okay, so I can go ahead and plot all these points, but I'm actually only going to need some of them. This is only when x is greater than or equal to -2. So I need to get rid of all the points of x when it's not greater than or equal to -2. So I'm getting rid of all the points to the left of 2. All right. And since it is or equal to, I am going to use a solid circle, and I'm going to connect forever to the right because it's x greater than 2, which means I am going to the right, and that is continuing forever. Okay. And that is another example of graphing piecewise functions. I will make a couple more example videos because these ones do take a little bit of practice. I will also make some application problems of piecewise functions because, believe it or not, this is used a crazy amount in our everyday lives, bulk pricing, stuff like that. It's actually used in computer programming quite a bit, conditionals and stuff like that. So this is very, very important material. And I just want you to know that the subfunctions, all the pieces within the piecewise, do not have to just be lines. They could be parabolas, they can be cubics, they can be trigonometric functions, okay? Any type of function can be in a piecewise, but since we're just starting out, I just want to take a look at lines, okay? So in the next couple of videos, we're going to be covering some more examples and application problems. I hope this was helpful. If there's any questions, please feel free to let me know, and I'll look forward to seeing you guys in the next video.